Alright, so welcome to the screencast for calculations and the chemical equation. Basically, this is going to be our stoichiometry unit, but we're also going to we're going to talk about the mole, how to calculate molar mass, how to do conversions. We're going to do empirical and molecular formulas, and then the last part's going to be really dealing with stoichiometry. So you're going to see how all of the stuff that we've been doing up to this point kind of comes together in this unit. So here's our essential question. Why is the mole an important concept in chemistry? So that's the essential question for this first section of guided notes. So what is a mole? The mole concept in atoms. Atoms are exceedingly small. I'm going to show you guys a video clip of atoms during class, and you'll kind of get a sense for how small they really are. But the unit of measurement for mass of an atom, like if we're going to take like how much does one atom weigh, is the atomic mass unit. That's abbreviated AMU. This is what you're familiar with on the periodic table. This is what we call the mass. That's reported on the periodic table. The unit of measure for the mass of atoms. Carbon-12 is kind of assigned as the standard. It was assigned a mass of exactly 12 AMU, and so it has 6 protons and 6 neutrons, and it was determined to weigh exactly 12 AMU, so it is the standard by which all the other ones are based off of. If you were to actually weigh it out on a scale or balance, 1 AMU is 1.661 times 10 to the negative 24th grams. So that is incredibly tiny. This number right here is not something that you have much concept of. So we just work in terms of AMUs because it makes it a lot easier to use this relative mass of AMU than to use the actual mass of 1.661 times 10 to the negative 24th. So a practical unit for defining a collection of atoms is a mole. A mole is just a counting unit. When we think of counting units, you can think of like a dozen means 12. Or a score means 20. An acre means 144. So those are just counting units. A mole is another one of those. So 1 mole is 6.022 times 10 to the 23rd atoms. So if I said that I had a mole of pencils, I would have 6.022 times 10 to the 23rd pencils. If I had a mole of people, or a mole of hair, or a mole of paper clips, it would be 6.022 times 10 to the 23rd. It's just a counting unit. This is known as Avogadro's number, and it's the basis for this concept of what a mole is. So if I had 2 moles, then I would have 6.022 times 10 to the 23rd times 2. But 1 mole of anything is going to be the 6.022 times 10 to the 23rd. We just tend to think about it in terms of atoms. It's much easier to use this kind of arbitrary counting unit than to give the actual amount of atoms that are existing in a sample. Okay. So molar mass is going to be something that we're going to use to relate moles to the actual mass of an atom to make it easier for us to work with. So 1 mole of an element corresponds to the mass of a mole of atoms in grams. When I say I have a mole of oxygen, how much does that weigh? That's going to be the molar mass. If I said go weigh me out a mole of sodium chloride, how much are you actually going to put on the balance or on the scale? That's what the molar mass is. So it's a way to take this unit of moles and relate it to grams. And the cool thing is you've been doing this all along. You get the value from the periodic table. So that value on the periodic table is really relative. It depends on what you're actually talking about. If you're thinking in terms of individual atoms, then we use the atomic mass units. That's what that unit means, or that number means on the periodic table. But if we're talking in terms of moles, that tells you how many grams 1 mole weighs. So it's very, or it gives us a lot of really good information, but it's relative. So if I said I wanted a mole of fluorine atoms, it would weigh 19.00, or sorry, 1 atom of fluorine is going to be 19.00 AMU. So if I just took 1 individual atom of fluorine, that 1 atom would weigh 19 AMUs. So I can think of it in terms of that. Or I can think of it in terms of a mole of fluorine atoms. So if I had 6.022 times 10 to the 23rd atoms, that would weigh 19 grams. So you can already see that we're going to take this unit of moles And we're going to use the molar mass to relate it to a unit that we can actually put on a scale in terms of grams. So 1 mole of hydrogen is 1.0079. 1 mole of oxygen is 15.9994. 1 mole of any element is the molar mass on the periodic table. So you just have to look on the periodic table. But why does it weigh a different amount? Why does a mole of hydrogen, which is still 6.022 times 10 to the 23rd atoms, weigh 1.0079 grams, whereas a mole of oxygen weighs 15.9994 grams? The reason is hydrogen generally only has 1 proton and 1 neutron, whereas oxygen is going to have 8 protons and anywhere from 8 to 10 to sometimes 12 neutrons. So the reason is oxygen is just bigger. That's why it's going, 1 mole of the atoms is going to weigh more. It's just like comparing 1 mole of pencils to 1 mole of people. You have the same number, but the mole of people is going to weigh more. So just a little review of chemical formulas, because when we start analyzing and doing stoichiometric relationships between things, you're going to have to know how to calculate the molar mass, not only for elements, but for formulas. So just a little bit of review. Remember that H2 is 2 atoms of hydrogen that are chemically bonded. So that's why you see that subscript of 2. H2O is 2 atoms of hydrogen and 1 atom of oxygen. And remember, if there's no subscript, that's an understood 1. If I had calcium hydroxide, anything that's outside of the parentheses is distributed to everything within the parentheses. So I have 1 atom of calcium, and then I would have 2 of the oxygen and 2 of the hydrogen atoms. Ammonium sulfate, again, whatever is outside of the parentheses is distributed within. So I have 2 atoms of nitrogen. I would now have 8 atoms of hydrogen, 1 atom of sulfur, and then 4 atoms of oxygen. So the cool thing is I could find not only the molar mass of each of these elements, but I can find the molar mass of the whole compound, figure out how much a mole of that whole compound would weigh just by adding all of the individual elements up. So that's what we're going to do. So the formula mass is the sum of the atomic masses of all the atoms. So you just figure out how many atoms there are for each element and look on the periodic table to find the mass for that element, and then you just add them all up. So the molar mass is the mass of 1 mole of that compound. And the cool thing is our units are in grams, so we have now related grams to moles. Our units are going to be how many grams there are in 1 mole. So what's the molar mass of H2O? You have 2 atoms of hydrogen. Hydrogen is 1.0079, so take that times 2, and then you just add that to 15.9994. You'll notice up here that there's some rounding, like the oxygen gets rounded up to 16, and the hydrogen gets rounded up to 1.008. It just depends on what periodic table you're using. I kind of have some of the masses memorized that I've always used, and so just for me, I always use the 15.994 for oxygen. But 16 is not going to make that much of a difference. You might have a slight error in your last digit or some variation within your last digit on the rounding, but for the most part, it's not going to make that much difference. I would just use the mass that's on your periodic table. So I want you to do these as practice. Go ahead and calculate the molar mass for this whole or for all of these compounds, and we will work through these in class together to make sure everybody knows how to do it. Again, here's some more examples. So we have chlorine, remember a diatomic molecule, so those diatomic molecules still don't go away. I told you they were going to haunt you. So instead of it being chlorine, it's Cl2, potassium hydroxide, and then beryllium chloride. So the next thing that we're going to talk about, because, we just can't get away from conversions, and you should have seen this coming when we start relating things like grams to moles, we also have a conversion between moles to atoms. So I can determine by using these 2 conversions, if I'm given a mass of something, of a compound or an element, I can determine how much those atoms actually weigh. Or how many atoms are there, depending upon what the question is asking me. So these are the 2 conversion factors that we're going to be using in this unit. Remember, this is very different than this is much easier than the conversions we did in the beginning, where you had a whole page of different conversions you could use. There's only 2 of them. So 1 mole is 6.022 times 10 to the 23rd atoms, and 1 mole is the molar mass. And where do you get that molar mass from? The periodic table. So we're going to use dimensional analysis setup, so your T boxes, to do these conversions. So here's some examples, and I'm going to let you guys try these. So if I have 3 moles of methane, CH4, how many grams do you have? So you're going to start with 3 moles on your line, and you're going to use the conversion of moles to grams, so you're going to need the molar mass. And remember, there's 1 sig fig, so your answer should only have 1 sig fig. So you can go ahead and try to do these conversions, and we will go over them in class. And then there's also these ones to do as well. So 5 moles of water is how many atoms? So going from moles to atoms. Going from atoms to moles. Going from grams to moles. And going from moles to grams. So there's an example of each type of conversion. There's 6 different conversions. There's an example for each one of these in this practice problem set. I will remind you that you need to enter the scientific notation correctly in your calculator. And use parentheses, because if you are dividing, the order of operations will end up being messed up, and you'll end up with the wrong answer. It'll multiply instead of divide. So you need to make sure and use your parentheses when you are doing this type of a conversion. All right, so that concludes this screencast for the mole, molar mass, and conversions.